In this video, we're going to compare the concurrency model of two programming languages, of Python and Haskell, and we will see who is the best of them. Let's start with Python. We will go to the python.org and we will use the latest at this moment Python version, the Python 10.0. Here I wrote a simple concurrent TCP server in Python. It receives some requests from clients and return the factorial numbers to the client. So the client, also I have a client here. The client is just send it ask the user for some number and send this number. So here we ask the number and send it to the server. So, and the server is receiving this number and do some processor bound job and write the result to our client. So this is what we do. We do the factorial. Okay, I use standard Python library math and use math.factorial function. Okay, now let's start our Python server. You can see that it started on this address and port. And let's do some requests. So I go to terminal and run my Python client with request 3. So I receive the factorial of 3, this is 6. Okay, I can send 5 and I will receive 120 and so on. I do my requests, but what if I create some request with big number? Okay, for example, 5 millions. Oh, we can see that our client waiting for an answer because there is many job the server need to do to calculate this big number factorial. Okay, but let's start the second client with small number. Okay, what if our client want to have small number request and 5? And you can see that I sent here 5, but I didn't got any response. Why this happened? Okay, this happened because our server is hang. But why it's hang? It hang because it's busy. Okay, the Python have the explicit concurrency, and we need to give up our control to the main event loop explicitly. But here, when we calculate in our factorial, the standard model, we didn't do this. All this coroutine is just hanging here, and there is no point of give up the control. We need to do some await. We need periodically do some await, but we didn't do this, and that's why it hangs. This means that all the clients with our small task need to wait while this big task will be done. It's very bad. This means that our service is just can process the response. Okay, and our clients will go away from us. Of course, they can fix this thing. How can this fix this thing? Okay, let's go to our server and rewrite this factorial function. We will rewrite it in a concurrent way. I call this async and def factorial. And to receive some number on input, and they need some accumulator here, factorial one, and we need to do some loop for number in range of 2 and plus 1. We need to do the multiplication of our accumulator with number. Okay, so we accumulate all this number, and we want to return at the end our factorial. Okay, and here in our factorial function we need time to time give up control to the main loop. How can they do this? Okay, we can, for example, count some another variable, for example I, and we start from 0, and in every iteration we need to increment this variable plus 1, increment it, and if our variable, for example, equal 100, we need to add it async here and do some give up of our loop. Okay, give up control to main loop. We sleep for 100 milliseconds. Okay, and of course we need to clean our counter. Okay, I think this should work. Let's change our standard. We don't need it anymore. Standard factorial, we need to rewrite it, and we need to elevate it here. So what will happen now? Okay, let's kill our clients and let's restart our server. So we can see that it's serving, and let's check for clients. So let's check for a small one. Okay, we received as expected our factorial, and for every small number we receive this. And let's run now big number again. Okay, we can see that we can send this, and server is busy now. And if we do the requesting some small numbers, we can see that they receive their result now. Okay, and they solve this problem. For do this, we need to rewrite the standard module, the standard function of the standard library factorial in async await. In async await style, and we done this. So, but I think this is not very good, because we need some strange logic here, which is too far from what the factorial actually do. Okay, and I think this is not very nice. Of course, you can say that you can solve this problem with some we bring this problem to the infrastructure layer. Okay, you can add some more. For example, you can run some more processes with Python, but also you limit it here, because every process costs some resources. Okay, and you can't create so many of these processes for every Python instance. But let's go to Haskell. Okay, here we have some client server implementation, and here is our server implementation. Okay, it is exactly the same as I drew in the previous video about writing simple concurrent TCP server with Haskell. But I do some modifications in client. Okay, so this is server, and go to the client. Here, what I do, I create some new function, request FIBO, which takes some number and run client for requesting this number. So here we just request this number via TCP, and here I define the main function of we take some bunch of requests represented in list. This is in numbers from 1 to 100. This is really a small job, and it can be easily done by to calculate these numbers. Any modern processor can done this very quickly. And for every of this number, we run regfibo in their own light thread. So let's run our server. I forgot to say that I add some one library here in packages.yaml. It's called monad.loops or monad loops, which I add this package here, and it allows me to import this module which contains this fork map m function. So let's run our server. Stack run server. They can see that it's serving on this address. And now let's go to our client and run stack run client. Oh, we can see that our client stopped its job, and we receive all these requests. We receive all the responses for every of these 100 requests. This is because we are small, and we can see that our client is finished our job and it exit here. But what if I at the head of this list add some header job, for example 5 millions, okay, and 500 and 5 millions. Okay, let's do some big numbers here. Will Haskell hang on this? Let's run. Okay, you can see that every of these small requests is calculated here. There is no hang, but Haskell didn't. The client didn't exit here because these two big jobs are still running. They're running, but Haskell can accept any new request here. So any small request will be received. Let's start another client and see what happened. Stack run client did the same tasks. Okay, and we can see that that client is also receive all its small tasks and hang on big tasks. And this is just hanging. It gives me some response here. So here I have some zeros. I don't know why. Maybe that's some mistake in the encoding of the data, but this is no matter in this video. The main point here is that Haskell use an implicit concurrency model, and we don't need to think about some explicitly taking control to our loop. Here is the implementation of our factorial. Actually, we can take the module from the function from standard library to calculate factorial, but in Python, we need to re-implement the factorial and use these strange things which has no any relation to factorial, okay? And this is why Haskell beat Python in concurrency model, okay? And this is only one of the advantages of this beautiful language. Okay, why this is possible? This is possible because Haskell is pure language and everything in it is expression. And the expression can be calculated in different ways. Okay, it can be calculated in different ways concurrently. And where is no mutable data, shared state, and Haskell can easily to take implicitly control loop from one coroutine to another coroutine and do it internally with the maximum possible performance. Okay, and the interesting thing that while I talking here, the one big task I think this big task is done much more quicker. So it's I see its result here, and it's done much more quicker than the first client received this. I think because this happened because Haskell can somehow cache pure functions, so the factorial of this big number can be cached and not calculate twice. So guys, I think you like this video, and if you like, push like button, push subscribe button, and write comments. We will continue to talk about Haskell in our next videos because this is awesome language.